Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Olaoluwa and I'm working usual physics. Now we'll be considering elastic properties of solids. In this topic we'll look at the Hooke's law, Young modulus. We'll do some experimental verification of Hooke's law and determination of elastic constant of a spring. And we'll also consider energy stored and work done in springs and elastic strings. Okay. When you talk about elasticity, when you hear the word elastic, what comes to mind? When something is said to be elastic, it means that when that thing is stretched and released, it will return back to its original position. So, when you say a particular material is elastic, it means when stretched to a certain point, when it has been enlarged, it has been stretched by a force, and it is set free, it comes back to its original position. Several people have taken their time to study this phenomenon of things being stretched and returning back to their original positions. And one of those people who did this research came up with a law which became known as the Hooke's law. The Hooke's law states that the force applied to a body or to a string or to a spring that stretches it is directly proportional to the extension of the spring. That is, F is directly proportional to E, where F is the force and our E there is the extension of the spring. The expression becomes F equals KE. Now this K here represents the stiffness of the spring. So we can say the stiffness of the spring is given as F over E. Now this stiffness of the spring talks about the chances of the spring. It also controls the chances of the spring returning back to its original state when it is extended. Our E can be calculated as the new length minus the old length. So the length after the weight has been applied, and the length before the weight has been applied or the force has been applied. So that's what gives us our E. Okay. The length after the force or weight has been applied and the length before applying the weight or a force on it. That's what gives us our extension. In a few seconds, a question will pop up on your screen to test your understanding of Hooke's law. To further study the effects of forces on springs and strings, that is extensible materials, there came the idea of Young modulus. To further study the effect of weights and forces on strings and springs, there came the idea of Young modulus. The Young modulus of a string is said to be the relationship. It expresses the relationship between stress and strain. It expresses the relationship between stress and strain, where stress is the amount of pressure which is exerted on the spring. The strain is a ratio of extension of the spring. In other words, stress is the force applied divided by the area, that is the amount of pressure. And now the area here talks about the area of the spring, that is the cross-sectional area of the spring. And strain is the extension divided by the original length. Now, the Young modulus the law of the Young modulus shows the relationship between stress and strain. So the original thing says that the stress acting is proportional to the strain felt. And when we put it all together, we have FA equals a capital E. This capital E represents Young modulus, and we can calculate our Young modulus as FL over AE. Now note this, the strain has no units because this is meter divided by meter. It's just a ratio of the extension compared to the original length, while stress is in Newton per meter squared because it's force divided by area. So Young modulus comes out as newtons per meter square. Let's take a question on springs. A spring of natural length 3 meters is extended by 0.01 meter by a force of 4 newtons. What would be its length when the applied force is 12 newtons? When we look at this, what we need to do is, of course, write out our parameters first. The first thing we have is a force acting, and force is 4 newtons. The length is 3 meters, and the extension experienced is 0.01 meters. Now let's ignore this first part. From this expression we have on the board, we can go ahead and try to calculate. What is the relationship between the force and the extension. Of course, from our Hooke's law, considering our Hooke's law states that F equals to KE, where our K is our spring constant. So we need to calculate what our spring constant is. And how do we calculate our spring constant? We need our F and we need our E. So we'll substitute them into the equation. So we can have our spring constant equals to F over E, which will be, our F is 4 and our E is 0.01. When we divide, we have 400 Newton per meter. 400 Newton per meter. Now with this information, we can proceed to calculating what our new length would be when a force of 12 newtons is applied. So how do we go about that? The first thing we can calculate is our extension when we have 12 newtons. How can we calculate that? Our F, of course, equals to KE. So E will be equal to F divided by K. Here our F is 12 and our K is 400. So that will give us 0.03 meter. So this is our extension, but that's not what we're asked to find. We're asked to find what would be the new length. So the new length would be the old length plus the extension, which is 3 meters plus 0.03 meters. And that will give us 3.03 meters. Experimental verification of the Hooke's law and testing confirmation or determination of the spring constants. The diagram showing on your screen right now shows the experimental setup for verifying the Hooke's law. Now you can see the meter rule and you can see the retort stand. You can see the spring being connected and a pointer being attached to the spring. Now different loads is being placed on the spring, that is on the holder, on the hook that is there. The first one will be placed, that will say something about 0.1 kilogram, maybe 100 grams. Then you increase from 100 to 2. You take, after taking the 100 grams, you take the measurement of what what the new length of the spring is at that point. Of course, you measure the spring before you start. that's without any load. Then you put 100 grams and you measure the new length of the spring. Then you put another 100 grams, making it 200 grams, and you take a measurement and you put another one, and you keep doing it like that, increasing it step by step and taking measurements. Now, on concluding, maybe you get to about 600 grams, you could stop and you can plot the information gotten there on a graph. Depending on what type of this thing it is. Of course, what you plot on the graph would be the extension of the spring. Practical verification of the Oakes law and the determination of the spring constant. On your screen right now, you'll be seeing a diagram that shows that an experimental setup that is going to be used. When you're done with the experiments, the data collected from the experiment will be used to plot a graph, and the appearance of the graph will be as what I have here on my board. You have the elastic region, that is from the origin source to this elastic limit. Now the elastic limit is the limit to is the point at which any extension after that point, the material no longer extend uniformly. The extensions that it will now start giving would be smaller compared to what it used to be, and this would maintain itself during the yield region. But at the yield point, the material will no longer return to its original state. Apart from the fact that it will no longer return to its original state, it will no longer expand uniformly at all. Any weight you place on it, it will just expand at its own will. It will have lost its elasticity a great deal. And the next major point is the maximum load. The maximum load point is the point at which the extension, anything you place on it, if it should weigh beyond that, it would have no extension. Rather, it might even tend to have a negative extension. That is, it might tend to be returning back instead of it expanding. And we have the breaking point. At this point, any load as high as that can actually break the spring. The spring lose total control. Now, more information will be provided on how to put your data together in the practical section of this topic. Energy stored and work done on springs and elastic strings. We all know that we always tell us that to calculate work done is always equal to force multiplied by the distance traveled by the force. So the same thing applies when it comes to springs. Work done in springs is force multiplied by the extension, since that is the actual the direction and the amount of distance that the force gets since it's the direction and the distance that the force gets the spring to move. So work equals to Fe. But also let's bear in mind that we also remember that there is also a potential to do work in every spring. That is why we talk about energy stored. And energy stored, which is also the same formula we can use to calculate work in spring, is also Fe. Energy stored and work done in springs and elastic strings. I haven't talked about extension and force and everything. We need to understand how much energy we can get, that can be stored, that can be kept, and how much work a certain spring can do. We already know that work done, W, equals to Fd. That's force multiplied by the distance in which the force moves. So the same thing applies here. W is also equals to Fe. Only a slight difference. The F here is an average force, but here there is no initial force, which ends up with half Fe. average force, majorly because we are introducing extension. We are putting aside the fact that there is still a part of the spring that is not being really taken care of, that is not being observed, that is not being put in our calculation. So we have FFE. And let us recall, when we talk about energy and we talk about work, we say they are always the same. Energy equals also half FE. And energy is stored, is processed inside, is the potential to do something. So you don't necessarily have to have a force pulling the spring for you to calculate the work done. Sometimes it can just be an energy stored, an energy processed inside the spring. And to calculate such a thing, you need to understand the spring constant. The spring constant shows us how much extension a force can have on the spring. So it shows a potential. And if we recall, we said F equals KE. So bringing F equals KE into the energy equation, we have E to be equal to half KE multiplied by E, which would give us half KE squared. So the potential, the energy stored inside the spring can be calculated as half KE squared or half KE. Same thing with the work done by a spring. Let's take a question on springs. A stone of mass 20 grams is released from a catapult whose rubber has been stretched through 4 centimeters. If the force constant of the rubber is 200 newtons per meter, calculate the velocity with which the stone leaves the catapult. First thing we do is to write out our parameters. The mass of the stone is given as 20 grams, which is the same thing as 0.02 kilograms. The distance through which the rubber has been stretched, E, is given as 4 centimeters, which is the same thing as 0.04 meters. The force constant of the rubber, K, is given as 200 newtons per meter. And we are asked to find velocity. This one seems a little tricky, but if we think and try to put things together, we can calculate how much energy is possessed by the rubber at this particular point in time, and we can calculate how much energy the stone would use to fly away. So that would be spring energy should be equal to kinetic energy, and spring energy is calculated by half KE squared. Kinetic energy is calculated by half mv squared. So we can substitute our parameters into the equation now. We have the halves can cancel out. Our K is 200, our E is 0.04 squared, our M is 0.02, and V is what we're looking for. So moving things around, we can have our V, making our V the subject of formula, equals 200 multiplied by 0.0016 divided by 0.02. When you use your calculator, you have V squared equals 16, so V will be equal square root of 16, which equal to 4 meters per second. Yes, please also always bear in mind, we had to bring in 2 different formulas of energy to solve this problem. We brought in the energy for spring energy, that's the one we just learned, and also brought in kinetic energy, which we have been taught in a previous class. And the kinetic energy formula, of course, is half mv squared, while that one of spring which we use is half ke squared. In this topic we considered elastic properties of solids, and we stated Hooke's law, which stated that The force applied on a particular body, on a spring or on an elastic body, is proportional to the extension of the body. We also considered Young modulus, and Young modulus said that there is a relationship between strain and stress acting on the body. Also, we tried to describe the experimental method to verify Hooke's law, which is also the way to determining the spring constant, the elastic constant of a spring. And we also considered how to calculate energy stored in a spring and work done in a spring. We came up with two formulas, which are E, that's energy, equals to half KE squared, and E equals to half KE. In a few seconds, some questions will pop up on your screen. Please attempt them. And if there is anything you do not understand, you can go over this video one more time. Thank you.